So, good afternoon, everyone. I'm here to present our recent progress in the implementation of an optical fiber frequency distribution via commercial DWDM system. So, this is the outline of my speech. I will talk about our objectives, some initial lab evaluations, initial tests in SUNET. SUNET is a network we're using. The most recent ongoing evaluation in the lab, and I will have some conclusions and outlook. But I will start with some conclusions of things we have learned so far. So, simultaneous time and optical frequency transfer is possible in the same optical channel, even though the frequency transfer is deteriorated. We also know that we have heavy interference from the power grid within our own campus installation. And we also tried to using 1310 nanometers instead of 1540, and it was a real challenge. So the objective for this work is to develop and evaluate a stabilized frequency transfer technique that will be operating in a real commercial communication network. It must coexist with data channels. It should use duplex fibers and unidirectional amplifiers. It should be operational even if there is an unknown symmetry of different magnitude in the connection. And the final solution should also have a real-time stabilized frequency output. So the reason for us to start this project was that we bought this laser of wavelength 1542 nanometers. It has a line width of less than a hertz. It's really impractical to move around since it's sensitive to temperature changes and vibrations. But we know that nearby universities and some other institutes in Sweden would like to have access to the light from the laser. And the only way to give them access to that is to transmit it through optical fibers. And in this case, we are kind of lucky since 1542 is one of the channels in the DWDM grid we're using. So we set up a simple experiment in the lab, an initial lab evaluation. We use the ultra-stable laser. We split off some of the light to a reference arm, and the rest we sent to an acoustic optic modulator, which transmitted it through 24 kilometers of fiber before we amplified it and split it off about 10% of light. We sent it back and created a beat node. In this case, we used lab spools of fiber. So this is humble results from that evaluation. As you can see, it's okay for a free running connection in its first stage. We have some daily variations. That's also very common for us. We made some instability measurements of some of the components in the setup, as of the acoustic optic modulator and the EDFA, and they didn't affect the final results that much. So now we know we can do it in the lab setup. So we contacted Swedish University Computer Network, and their aim is to provide Swedish universities with well-developed and effective national and international data communication and related services. So this project sorts under related services. So this is a map on their network. We have a connection to it. And one of the nearby universities I was talking about is Chalmers University in Gothenburg. It's about 60 kilometers away from us. They're also connected to SUNET. And we know that the photonics group there would like to have access to our laser. So we set up a real first test in SUNET, and since it's a live network, we are not able to break the light or something like that. We always need to have light on our channel, otherwise we will interfere with the channels besides us, which means that in this initial real test, we used the acoustic modulator in the reference arm instead of the transmitting path. So we use the same laser, we split off the light, we send it amplified it, and we had some excess fiber of about 2 kilometers, sent it through the whole of SUNET, up to Chalmers, split off about 10%, amplified it, and send it back through another fiber, which means we are using 2 fibers. And when it returned to our lab, we get a bead note. This is the communication network that are sending in the channels besides us in SUNET. Up here, we have EDFAs and splitter and filters and so on for our experiment. So this is a result from our first test in SUNET. As you can see, we only have 6 hours of data since some equipment broke. It's really noisy. And down here, you can see it varies between 73 to 75 megahertz. So that's not good. We also took out the best part of it here and saw that, okay, it's not that bad. So what is the best we can do without having any more equipment into the experiment? So we made an overlapping Allen variance plot of it. And it's kind of okay, I think, for not being a stabilized connection in its first stage. But we couldn't settle with that, so we know we have a lot of noise in our connection. So we thought, okay, we need a phase-lock loop. So we created a really simple one. It's just using just the gain of it. We used an ordinary signal generator. We had a mixer. And we introduced it to the system. And since it already were down, we were able to move the acoustic modulator to its right place. And here, up here, we have a picture of it. And then we got about 6-7 days of data. And as you can see from the black graph here, it's still rather noisy. And it's the results before the phase-lock loop and afterwards. We have it in red, and we still got the significance of the signal. So then we thought, okay, we got to do a round trip measurement of our connection. So we blanked out about 25 microseconds of the feedback to the acoustic modulator once a second, which means we get a 1 PPS pulse. We started a time interval counter on the transmitting path, and on the returning path, we stopped the time interval counter. And we got this measurement here in red for about 6 days of data. As you can see, the time difference is about a millisecond. It's not just optical, it's included electrical delays in this number. So we also performed a moving average about 10 minutes, here shown in black, to see if we have any daily signatures on our system. And it's not really that clear if we have that. We also performed some Allen plots of it. And up here you have the plot with including the 1 PPS modulation. As you can see, it's worse than that one without the 1 PPS modulation. So it was like expected. We know we are affected by several things on our connection, so we thought, okay, we need to know if temperature somehow affects it. So we took the frequency data from the connection of the 6 days and plotted it against the outdoor temperature nearby our location, and we couldn't see any significant correlation of it. And we also performed it with a time difference measurement, but still, it doesn't seem like the temperature is a big issue for us in this case. Then we knew we have some interference from 50 Hertz. So we set up the Chalmers connection again and locked it to the AC line using a polarization beam splitter, which take in the light and split the light up in 2 polarization states. And we looked at it on an oscilloscope. And down here we can see a clear pattern that we have 50 Hertz interference from the power grid. And up in red here is a summation of the two polarization states. So if we move one of them, it should be as before. It should be continuous. So this might be the problem. We are mixing power cables and fibers, and our fibers run through our transformer station, which only generates about 3 times 400 volts and about 3 times 1,000 amps. So that's kind of much. So this could be the Faraday effect, but I don't think the Faraday effect would affect the fiber that much that we are seeing. So someone suggested that the cable ladders might be vibrating at 50 Hertz. We haven't done that measurement so far, but we will do it and see how we are affected and why we're affected by 50 Hertz. But in the meantime, we set up an experiment in the lab. We took down about 80 kilometers of fiber spools to the lab, performed the same experiment with a pulsation beam splitter. And as you can see from the result, we don't see any clear pattern of 50 Hertz as we could see before. So now we know that somewhere along the path 50 Hertz is introduced to our system. Then we had a 1310 nanometer laser in the lab, and I was a bit curious to see if we could introduce 50 Hertz to the 1310 as well. But just to set up an experiment, set up an equal system like the 1542. We also introduced an amplifier, showing down here. We placed about 80 kilometers of fiber spools on the roof to have some temperature variations on them to see if something was varying. It didn't go that well, so in the first 6 hours it worked, then it got really worse. And yeah, it's a common problem since we know from the school books that fibers and 1310 nanometer are affected by humidity, and it was really humid outside during this period, and we also measured the attenuation of the fiber. It's doubled, so that's why we couldn't get it to work at 1310, and we got it working at 1542 since it's not that affected by humidity in that wavelength. So we set up the same experiment. We took some new fiber spools and set up it in the lab. On the right y-axis, we are showing the 1542 nanometer, and on the left y-axis, we're showing the 1310. And it was kind of noisy here in the beginning. We are not using phase lock loop in this case. I don't really know why it's behaving like this, so we have to investigate that a little more. And it's saddled sometime here. As you can see, the 1310 is a lot more noisy. It's maybe dependent of its line width. It's a couple of megahertz. And also, we got loss of signal for some time, and we got this big jump. So I have to investigate that. I did a brief investigation, just plotting the temperature in the lab. And it's an unstabilized lab. It's kind of new. We just have it like an extra spare lab. And the temperature wasn't that good. We can see some patterns. If you place a temperature plot against the measurement plot, you can see this V shape on the 1310. And if you inverse the beginning of the temperature here to the 1550, it might be affected by it. I really don't know so far. So the conclusions and outlook. The experiment has so far shown that it's possible to perform a coherent optical frequency transfer in commercial DWDM network and coexist with other data channels without making any big changes to the network. But to achieve auto stability to the connection, it must be actively stabilized. And still, it's a work in progress, so future work includes the focus on phase-locked loop and stabilization and so on, and also have a further look on polarization changes and challenges. So I would like to acknowledge SUNET, Post and Telecom Authority, and Swedish Governmental Agency for Innovation Systems.